Assalamualaikum warahmatullahi wabarakatuh. My name is Farisha binti Rosdi and my friend is.
And my name is Syuhada binti Rozain.
Today we want to present about the logic of motion, which is
Mathematics and computational thinking in optimization.
Good morning to my lecturer and my fellow classmates. Today I will be presenting on the intersection of mathematics and computational thinking in the field of optimization. In our modern digital era, the ability to move goods and services with extreme efficiency is no longer just an advantage. It is a fundamental necessity for both global businesses and everyday consumers to remain competitive and meet high demands. Companies are under constant pressure to deliver products at high speed while simultaneously achieving three critical goals: minimizing operational costs, reducing travel time, and lowering fuel consumption. The complexity of this logistic system is immense, but mathematics provides the essential logical framework required to model these real-world challenges. By using mathematical principles, we can transform a chaotic network of deliveries into a structured system that can be analyzed and optimized systematically. One of the most significant and widely recognized mathematical applications used to address this specific logistical challenge is the traveling self-person problem, which is TSP. At its heart, the traveling self-person problem seeks to solve a very specific puzzle. How can we determine the shortest possible route that visits a predefined set of locations exactly once and ultimately returns to the original starting point? This problem is deeply rooted in graph theory, a specialized branch of discrete mathematics that focuses on the intricate relationships between various points and their connections. Within this mathematical model, we use specific terminology to represent the real world. Note, this represents specific physical locations such as cities, warehouse, or individual delivery stops. Edges also, this represents the actual paths or routes that connect one route to another. Weight is every edge is assigned a numerical value or weight, which represents a cost factor, most commonly physical distance, travel time, or even monetary expense. The practical process of solving this problem begins with the collection of input data, which might be specific coordinates or a detailed distance matrix showing the gaps between every location. From there, advanced algorithms are applied to evaluate every possible route to determine the single most efficient path. The final output is an optimized route that ensures minimal travel distance or time. This is not just a theoretical concept. This mathematical approach is the backbone of real-world delivery giants such as Amazon and DHL. Without the use of sophisticated mathematical models and algorithmic reasoning, the task of managing this vast global delivery network would be nearly impossible for human operators. This clearly demonstrates how mathematical logic serves as the primary support for modern computational systems in solving our most practical and complex everyday problems.
Okay, so now let's move to solving complex real-world problems. As we know that mathematics play a major role in solving problems that are simply too complex for humans to manage manually without the aid of structured systems. One of the most significant challenges currently facing global logistics systems is the overwhelming number of possible delivery routes that must be considered to ensure efficiency. As the number of delivery stops or locations increases, the total number of possible routes grow at an extremely rapid pace, following what is known as vectorial pattern. Alright, to understand the scale of this complexity, we can look at the following example, which is when a delivery driver is assigned only 5 locations there are already 120 possible routes to evaluate. If that number increases to just 10 locations, the number of possible routes exceeds 3 million. At 50 locations, the possibility explodes into the billions, making it monumental task for any human to break the process. Because of this rapid and massive growth in data, manually checking every single route to find the best one becomes a physical and mental impossibility. This is where the medical modeling becomes essential, as it allows these complex routes to be represented visually and logically using graphs. In this graph, each physical location is represented as a node, while every row or path is shown as an edge that connects these nodes together. Each edge contains a specific weight that represents as cost factors, such as the total distance or the travel time required to cross it. Okay, so by using this model, computer can evaluate millions of roads efficiently to achieve a common mathematical objective in route optimization, minimizing the sum of the distance represented by the formula, which is sigma Dij, where Dij is the distance between the location I and location J. The capability helps organizations significantly reduce their fuel usage, lower their overall operation costs, and improve the general efficiency of their delivery service. Ultimately, mathematical optimization transforms what would be chaotic and complex decision making into structured and reliable computational process. Beyond the basic calculation of routes, solving these complex problems requires a deep understanding of dynamic variables. In a global logistic environment, the weight of an edge is rarely static. It is constantly influenced by external factors such as real-time traffic congestion, road maintenance, and even weather conditions. Therefore, the mathematical model must be robust enough to handle this fluctuation by integrating real-time data into our graph model. We move from static optimization to dynamic optimization, allowing for adjustment on the fly. Furthermore, the impact of solving these complex problems extends to environmental sustainability when we successfully minimize the sum of distance using the toilet. We are not just saving money, we are directly reducing the carbon footprint of the entire logistic chain. Fewer miles traveled means lower CO2, which is carbon dioxide emissions, and less wear and tear on infrastructure. This aligns mathematical efficiency with global green initiative, proving that computational optimization is a key driver for sustainable development in the 21st century. Okay, so finally, the transition from manual decision making to structured computational process allows for better scalability as a business tool for delivering to 10 house to 10,000 house. The human mind reaches a breaking point almost instantly. However, through the power of mathematical algorithms and high-performance computing, this system can scale indefinitely. This scalability is what allows digital platforms to manage global supply chains with precision, ensuring that the right product reaches the right person at the absolute lower cost to society.
Okay, next we move to computational thinking in action. While mathematics provides the essential theoretical foundation, it is computational thinking that effectively acts as the bridge, transforming these abstract mathematical models into practical, scalable solutions for the real world. Computational thinking is not merely about writing code, it is a high-level problem-solving process that involves breaking down complex logistical challenges into manageable logical steps that a computer can execute with extreme precision and speed. In the context of the traveling salesperson problem, which is TSP, and route optimization, we utilize four fundamental pillars of computational thinking to streamline operations. Okay, for the first one is decomposition. This pillar involves the strategic process of breaking a massive, overwhelming problem into smaller, more focused sub-problems. In a real-world scenario, a logistics company may find it impossible to optimize a million delivery points across an entire country simultaneously. By applying decomposition, the company can divide its operations into specific regions, city zones, or delivery clusters. This makes the optimization task significantly less computationally intensive and allows each sub-region to be handled independently and more accurately. Alright, for the second one is pattern recognition. This concept focuses on identifying recurring trends, similarities, or regularities within the delivery data. For instance, by analyzing historical data, we can recognize consistent patterns such as clusters of customers residing within the same high density residential area or commercial hub. By identifying these patterns, we can group deliveries together into specific routes, which drastically reduces redundant travel distance and prevents overlapping paths, leading to much higher operational efficiency. Okay, for the third one is abstraction. Abstraction requires us to filter out the noise and focus exclusively on the core information that directly affects the solution. When building a mathematical model for road optimization, details such as the color of the delivery bag, the driver's name, or the specific brand of the vehicle are completely irrelevant. We abstract the problem by concentrating only on the essential variables, the precision distance between points, the connectivity of the road network, and time constraints. This simplification allows the algorithm to run faster without being pulled down by unnecessary data. Okay, for the last one is algorithmic thinking. This is the final stage where we define a specific step-by-step procedure or set of rules for the computer to follow to reach solution. A well-known example in this field is the nearest neighbor algorithm. This is a heuristic approach where the computer is programmed to repeatedly select the nearest unvisited location as the next stop in the sequence. While a heuristic like nearest neighbor might not always guarantee the mathematically perfect or absolute shortest route, it is capable of generating highly efficient and good enough solutions in a fraction of a second in the fast-paced world of real-time logistics, where thousands of new orders are processed every minute. This speed and reliability are far more valuable than a perfect answer that takes hours to calculate. So, the true power of computational thinking lies in the seamless integration of these four pillars. When decomposition, pattern recognition, abstraction, and algorithmic thinking work in harmony, they allow us to move beyond simple one-off solutions to creating a robust system of continuous optimization. For instance, in a modern delivery ecosystem, these computational steps enable a feedback loop as the algorithm executes a route. Real-time data is fed back into the system, allowing the pattern recognition pillar to identify new traffic trends or delivery delays instantly. This illustrative process ensures that the mathematical model remains relevant even in a volatile environment. Furthermore, this approach democratizes high-level logistics. Even small-scale enterprises can now utilize these computational frameworks to compete with global giants. By shifting our focus from finding the perfect answer to building a logical process, we empower technology to handle the heavy lifting of decision making. Ultimately, computational thinking is the engine that drives the efficiency of our digital economy, ensuring that the complex logic of motion is translated into seamless, everyday convenience for everyone.
Okay, so now let's move to mathematical example of root optimization. So now, to truly understand the operational mechanics of trigonometric personal problem, let us examine a concrete mathematical simulation involving four distinct locations labeled as A, B, C, and D. In this scenario, we assume that point A is our primary distribution center or the starting point. The challenge is to find a Hamiltonian circle a route that visits every other node exactly once before returning to point A. By systematically analyzing the distance provided in a distance matrix, we can evaluate and compare the total cost or distance of various permutations. Now, let's look at the breakdown of four potential combinations. Root 1, we have A, B, C, D, A. By summing the specific weight of each edge in each sequence, we reach a total of 25 units. While root 2, A, B, C, C, A, these alternative sequences utilize different edges, resulting in a significantly lower total of 80 units. Root 3, A, C, B, E, A, similar to the first root, is specific spacing configurative also totals 95 units, indicating it is not the most efficient choice. And lastly, root 4, A, C, B, E, A. Finally, this sequence mirrors the efficiency of root 2, also totaling 18 units. Through the comparative analysis, we identify that the shortest possible distance is 80 units. While a human can solve 4-node problem on a piece of paper, the true value of this mathematical reasoning lies in its scalability. Modern logistic computers perform this exact type of evaluation on a much larger and more complex scale every second, processing thousands of nodes simultaneously. This example perfectly demonstrates how logical deduction and mathematical precision allow us to identify the single most efficient solution among an astronomical number of possibilities, ensuring that resources are never wasted. To provide a deeper mathematical perspective, this optimization process is fundamentally governed by the objective function of minimizing the total distance expressed as z equal to sigma dij. In our example, the identification of root 2 and root 4 as the optimal solution is not a more coincidence. It is the result of systematically evaluation. When we look at the distance matrix, we are essentially looking at the weight graph where the cheapest edges are prioritized to form the closed loop. This mathematical deduction is what allows logistic companies to achieve significant marginal gain. By choosing a route that is 50 units shorter, as seen in our comparison between 95 and 80 units, a company can scale its saving across thousands of trips daily. This translates directly into thousands of liters of fuel saved and a massive reduction in engine wear and tear. Therefore, the simple calculation we see here is the foundation of high-level industrial strategy, proving that in the world of motion, the shortest path is always the most logical and sustainable choice.
For the next one is important in modern industry. Mathematical optimization is no longer just a luxury, it has become an absolute necessity in the survival and growth of modern transportation and logistics industry. In an era of cheap profit margins and high competition, even a small improvement, perhaps just a 1% or 2% increase in loading efficiency can generate significant financial savings for a company. When scouts across a fleet of hundreds of vehicles, These marginal gains accumulate into millions of dollars in saved operational expenditure. Beyond the direct financial benefits of saving money, optimized routes provide a cascade of advantages that strengthen a company's market position. First of all is reduced fuel consumption. By identifying the most direct paths and avoiding unnecessary mileage, companies drastically lower one of their highest variable costs, fuel. This also reduces the mechanical wear and tear on the vehicle fleet, extending the lifespan of their assets. Improve delivery speed. In the issue of instant gratification, delivery speed is a major competitive differentiator. Mathematical algorithms ensure that drivers spend less time in traffic and more time completing deliveries, ensuring that products reach consumers in record time. Next is increased customer satisfaction. Precision in routing leads to more accurate estimated time of arrival, which is ETA prediction. When customers receive their packages exactly when promised, brand loyalty and trust are significantly strengthened. Environmental sustainability, perhaps most importantly, optimized routes lead to lower carbon emissions. By reducing the total distance traveled, companies directly support global environmental sustainability goals and contribute to a greener planet. As digital technologies such as the Internet of Things, IoT, and Big Data continue to evolve, the critical role of mathematics in managing these industrial systems will only continue to grow. It is the engine that allows modern industry to remain agile, profitable, and responsible in a rapidly changing world. Moreover, the integration of mathematical optimization within modern industries acts as a catalyst for the digital transformation of global supply chains. In a world where data is the new oil, these mathematical frameworks allow companies to turn raw information into actionable intelligence. By utilizing real-time optimization, businesses can achieve a level of agility that was previously impossible. For instance, if a sudden route closure occurs, an optimized system can reroute an entire fleet in milliseconds, preventing a domino effect of delays. Reliability is what underpins the success of the on-demand economy, whether it is e-commerce, ride-sharing, or emergency medical logistics. The precision of mathematical logic ensures that resources are allocated exactly where and when they are needed. Furthermore, as we move towards an era of autonomous vehicles and drone deliveries, these algorithms will become even more critical, acting as the brain that coordinates thousands of unmanned units safely and efficiently. Ultimately, the importance of this field lies in its ability to harmonize economic profitability with social responsibility, proving that smart mathematics leads to a smarter, more connected world.
Critical evaluation and modern function. While the mathematical choice we have discussed are incredibly powerful, we must evaluate them critically within the context of real-world limitation. The most significant theoretical hurdle is that the Trevelyan-Stephenson problem is clarified as an SPH problem. In simple terms, it means that there is no known algorithm that can find the perfect solution in a reasonable amount of time as the number of locations grows. The computation time does not just increase, it explodes exponentially. For a global logistic network with thousands of nodes, searching for the absolute shortest route would require a computational resources and time that exceeds current technology capacity. As a result, modern industrial systems must often pivot away from seeking a perfection and instead rely on heuristic or approximation algorithms. This method, such as heuristic algorithm or end colony optimization, are designed to prioritize computation computational speed and practical efficiency over 100% mathematical accuracy. This creates a perpetual trade-off. Do we spend hours of computing power to save a few extra meters, or do we find good enough work in milliseconds in the fast-paced digital economy? The latter is almost always the preferred choice. Furthermore, we must address the modern concern that a static mathematical model cannot easily predict. In the real world, a short path on a map may not be the fastest path in reality. Mathematical models must now be dynamic, adapting continuously to unpredictable variables such as sudden traffic congestion, accident or peak hours that turn a clear highway into a bottleneck. Second, potentiality weather conditions, storms or floods that can make certain geographical areas completely impassable. And lastly, fluctuating demand, last-minute order or cancellation or urgent instant delivery request that force the system to recalculate through mid-journey. Ultimately, the practical implementation of the PFP requires a constant and delicate balance between theoretical accuracy and computational feasibility. We are no longer just solving a puzzle on paper. We are managing a living, breathing system that requires mathematics to be flexible as the world seeks to optimize. Beyond these physical and computational hurdles, we must also consider the integration of human factors and regulatory constraints. Modern logistics is not just about the shortest distance. It must also account for driver-specific regulation, specific delivery windows, and urban access restrictions. This soft constraint adds another layer of complexity to the traveling six-person problem, transforming it into a physical routing problem with a time window, which is we call VRTCW. This requires our mathematical model to not only be fast and dynamic, but also high constrained by legal and safety parameters. Furthermore, the reliance on real-time data introduces the challenges of data integrity and connectivity. If the sensor or GPS system providing the live weight of our graph edge fails, the entire optimization process could lead to inefficient or even dangerous routing. Therefore, a critical evaluation of this system must include a decision on resilience, how the system performs when data is incomplete or inaccurate. Ultimately, while we strive for the highest level of efficiency, the modern constraint of uncertainty means that our mathematical journey is never truly finished. It is a continuous circle of monitoring, recalculating, and adapting to a world that never stands still.
As we reach the end of our discussion, Nia, I am struck by how invisible yet indispensable these systems are. We have talked about the math and the logic, but how would you sum up the real-world impact of mathematical optimization on our society today?
That's a great point, Farisha. In conclusion, mathematical optimization has moved beyond the classroom to become a vital pillar of our modern digital society. Whether we are ordering food through an app or waiting an online shopping delivery, we are essentially relying on this complex algorithm to function seamlessly in the background. By integrating mathematics with computational thinking, we empower computers to analyze massive data sets that would be impossible for humans to process, allowing us to determine highly efficient solutions in real time.
It really changes the perspective on test and delivery, doesn't it? It's actually a massive computational feat. If we look at the specific benefits, would you say the impact is mostly economic?
Academics is a huge part of it, definitely. This technique allows business to significantly reduce transportation costs and improve overall delivery performance. However, the impact is much broader than just profit. One of the most critical outcomes is how it minimizes environmental impact by finding the shortest, most efficient routes. We are directly reducing fuel consumption and carbon emission. This proves that mathematics is far more than just a theoretical subject found in textbook. It is a practical living tool that is actively shaping our digital society and providing the keys to solving complex global challenges.
I agree. It's inspiring to see how a mathematical framework like the traveling salesperson problem can lead to a greener and more connected world. Thank you, Nia, for sharing these insights. It's clear that as our technology continues to evolve, the synergy between math and logic will remain essential for our future.
Wait, Farisha, before we wrap up, I actually have one question for you. We have discussed how this system help big company, but how do you think this is integrating of math and computational thinking actually empower the end consumer or the regular person on the street?
That's a thoughtful question here. From my perspective, it's all about reliability and accessibility. When we use these algorithms to analyze large datasets, the result for the consumer is a service that is not only faster but also more predictable. For example, the accuracy of our estimated time of arrival, which is ETA, when tracking a parcel is a direct result of route optimization. It reduces the frustration of waiting and builds a deeper trust between the digital provider and the society it serves.
I totally agree. It's like the mathematics is acting as a silent guarantee of quality. But looking at the bigger picture, Farisha, do you think these mathematical tools are just a trend for current technology, or are they here to stay?
I believe they are far more than a trend. As our digital society continues to evolve with emerging technologies like AI and autonomous drones, the need for these mathematical frameworks will only grow. We aren't just solving today's problems, we are building the foundational logic for future innovations. It's about solving complex global challenges. I believe they are far more than a trend. As our digital society continues to evolve with emerging technologies like AI and autonomous drones, the need for these mathematical frameworks will only grow. We aren't just solving today's problems, we are building the foundational logic for future innovations. It's about solving complex global challenges like urbanization and resource scarcity through the power of optimized motion.
Exactly, it really drives home the point that mathematics is practical tool shaping our world. It's not just about finding X in the classroom, it's about finding the most efficient way to move our world forward.
Well said, Nia. I think we can both agree that the synergy between mathematical theory and computational thinking is what will keep our modern industry agile and responsible for years to come.
That's all from me. Bye.